reasonably well-established field, and methods from it, such as superficial homology combined with persistence, are sort of very well-established and often even applied by people with no mathematical experience at all. So Professor Wu is a well-known pure mathematician from fields of homotopy theory and algebraic topology, and but more recently he's moved over some of his research to considering more advanced mathematical ideas of applying topology to various different fields. So it'd be very nice to hear from him today about some of his recent progress. Let's welcome him.
Okay, so thank you. First, I want to thank the organizers to give me this opportunity for giving a display and lecture, right? So the lecture I'm trying to address these questions, the question about the AI, right? So the fundamental question, because I'm from the area of topology, right? There's some fundamental questions. So what should the area of topology do, and how to interact with the AI? Right? Of course, this is only my personal views, and everybody have different views, right? And also, I display a little bit from some works in this direction of being a team. So we have a group of people working in this direction. Okay, so my talk will be basically make in 3 sections. Okay. So first part I try to, because I try to think about what the topology and the another side is AI, right? So it seems there was something now is quite hot, so-called AI for mathematics, right? So I would say the first view, maybe we still have to think from the view of topology. So what the AI for topology can do, okay. Now, second thing we will think about in another direction, right? Now, what the topology can do for AI, okay? So, and finally, I will display some works our team members, and they make some practical applications, use topological approach. Okay, so now let me start with AI for topology, right? So well, AI for mathematics is popular to people now. I think people did a lot of excellent work in this direction. Now, to me, I'm more interested in this from my area. It's from the algebraic topology, right? So I would say I'll try to guess, right? So what can we do for AI to help? Well, here's the display possibilities of something, right? So the core notion in algebra topology are homotopy groups. So we want AI should do something for challenging mathematical questions, right? So we can expect the possibility they can, of course, can help computing homotopy groups. That could be possible because there's a spec sequence they can compute, so you can help. And I think it can do more, so you can try to look at the structures of homotopy group. And therefore, try to follow some other people's ideas. So look at what you already know for computing, and you expect a certain structure. And then leave mathematicians try hard to prove it, right? So that could be a direction. And you can observe whether there's any special patterns in the spec sequence. Actually, the spec sequence, if you display that, there are some patterns. So you can raise some new mathematical questions on that. That would be, I would display a little bit. Actually, there are one of our members, actually, the Bingsen, was working this direction, I was saying that. So now another thing would be, how can we use, say, mathematics to help the AI, right? Of course, let's just from my understanding of this part. Well, mathematics may help for scientific interpretations when you do if you purely use, say, any models like language model or anything. Seems if without mathematics, it could be like get a very excellent result, but the missing part is that for human beings try to understand what the laws laws in the natural world instead of like we just say somebody tell us here it is, right? So that mathematics definitely will be used, and of course mathematics can help improving the computation. So we want to help improve. There's one question actually nowadays, if you take a large language program, you can try to say, okay, it will cost a lot of money, right? So whether you can reduce it, you use a smaller program, but use some mathematics to get the same result. That would be one trend. And the mathematics can be to get some features on the data. So if you give it data, you can look at some rows out of that. So math can try to get some feature to simplify it. In the big data, it's huge, but some important feature, and try to use that to classify data to predictions, and that could be the low. And the math can be used to try to build up, say, some new learning models, right? Actually, the learning model actually now is also like transformer is used a lot, but the diffusion model is also people use a lot as well, and you can improve that. So anything you can do that, and it will be a last one I would say. To me, it's really interesting whether we can develop some new mathematical series motivated through applications, right? Because nowadays we are moving to AI times, then there should be some mathematical theory. Well, for future new ones, we hope to get something that's like for new mathematics out of that. Okay, okay. So now let me say a little bit. So now let's say there's some few things. So like there are some fundamental problems arising from well, at least a few fundamental problems, right? And the big data actually brings the complexity of word to the science. Well, data itself is it's a big no, it's a size, big complex on that. So we need to understand the structures of that, right? Also, like the AI. Well, if you use AI, if the AI departures from the this domain expert, then of course we get a less understanding. Even you get a good result. So that's exactly we need some gap. So math try to fill in the gap. So we need to understand what's the background domain expert supposed to be, right? Okay. So also actually by chatting with many people working experts in AI, well, they also demand or try expectations from mathematicians to get some new science for AI. Right? Okay, so now let me move to the first one. Okay, so yeah, here I see this talk I will say aim to general audience. So I just briefly say idea, and the first one I think many people already know because it published already a few years ago in Nature paper, and that could be like example how the AI can help mathematics, right? Well, the question the authors was pick up some good questions in knot theory, so these volumes, and through here's the basic few ideas how they do, right? So from these data, they can try to formulate it. Well, first of all, something can be related together, so try to find some connections, and then from these connections, use this data, try to make a formula. So the formula should be like the volumes of the hyperbolic knots. Actually, there's address an important question in knot theory. Okay, and then you try to, or your mathematician can really prove that. So that shows success that AI can really help like math. Well, as I said, yes, actually we are also working on this one. So like Fedor Pembesky is assistant professor of our Binzer, so it's in our team. And we are working on algebraic topology. So there's a question will be, can we do something, for use AI to do for homotopy proofs? Of course, this is the, so there's one project the fellow is working, now he carried out some result on that, okay? So the, well, let me show you a little bit, then I try to maybe explain mathematics, background mathematics questions, right? Because most of us here are mathematicians, so I try to do that. Now, so the way they try to, I say, roughly say here, right? So there's a formula which can be give like a, describe the homotopy group of two spheres in terms of something in combinatorial group theory. So you get some free group and letters, then there are some canonical subgroups out of that, and then you have formulas. So I will explain a bit further. Okay. So now this one and the project tries to say, okay, well, I can use language program to help to do that, right? Okay. So now here's a procedure Fedor was working. Okay. So they designed some information like that. Okay, so the key point, because now at the moment you can see that yes, for free group, there are certain subgroups, and you need to understand some intersection of these subgroups. So how can we find it? And you need to quotient out certain commutative subgroup. I will explain, okay? So in other words, you have one is you really need some intersection. So if free group, you get one subgroup, another group, how to work out the intersection, like equations. Words belong to this and belong to that, right? And the important thing is that when this quotient out certain commutative subgroup, this exactly given the homotopy group, okay? So the question, okay, so now you need to use some program and try to design it. Okay, so now what details, of course, you can read the paper of that. Okay, so here's the information of how the concrete information about this formula in terms of mathematics. Okay, so now let's say the following. So you get a free group of n letters, right? So you get x1 up to xn. But the indexes, we get n plus 1. So say R1 means the normal closure of x1. So you take x1, you take all conjugations on that, and generate a subgroup. That's it. And R1, R2, and Rm is okay, but there one extra element you need. So this extra element, you just take product of all these elements, okay, from x1 up to xn, and let's call x0, right? So this x0, just product elements, and do the same procedure. So you take a normal closure. So that means you take any words, take a W, say x0, W inverse, okay, make a conjugation, and generate a subgroup. That's it. And then you can try to do the commutative subgroup, because each of, say, R0 and R1, you can take commutative subgroup, right? And you can take commutative with R2, so you get a 3 for the commutative, the 4, 5, and keep it so. Then you try to permute all indexes, okay? So this group, as you see that, at least you can know the generators, because when you take a commutator, you know the generators, okay? So more or less, we say this group is understandable, okay? In this sense, we know how to construct the generators. And now you can do the similar procedure. You make a copies of that. So you take x1 up to xn, then take a y, just a copy of that. Okay. Now you take a pairing. So say R1, you just take a x1, y1, you take a normal closure. Okay. And R2 and so on and so on. Now you have x0, y0. Okay, take a normal closure. So that you get a similar subgroups of the free group. And now it's a rank of 2n, right? Okay, now and also you have symmetric commutative subgroup. Okay, it should be missing S. Okay, so we talk about symmetric commutative subgroup. Now, okay, so now here's an interesting point. Okay, when you do this one, so you can do the intersection of these n plus 1 subgroups. And then just quotient out by the symmetric commutative subgroup, right? Okay, so this gives the first formula. And this is a homotopy group of S2, right? But maybe some of you maybe are not happy, particularly a lot of graduate students. You say, oh, well, we want to understand the stable homotopy group of sphere. Well, okay, let me tell you there's another way to see stable and unstable everything. How can you do for spheres? Well, I just take 2 copies of S2. Okay, so that's it. And the formula you use another one. So I take a free group rank of 2. Now this will give us a homotopy group. Yes, the general M. Okay, homotopy group of S2 wedge S2. Now, why I say this is good? Well, the homotopy group of the S2 wedge S2 contains all possible homotopy groups of any dimensional spheres, whatever, stable, unstable, everything here. So this is actually, you can see, monster homotopy group, packing everything inside. Okay, it is actually it's good, important, and the S2 wedge S2 just 2 balls joined together, right? Everybody understands, but it is in depth, contains everything homotopy theory. Okay, for concerning homotopy group of sphere. And the way to see this pattern, you just look at the Hilden-Milner theorem. You will see that. Hilden-Milner theorem will tell you that you get decompositions. So any higher homotopy groups of any dimensional spheres, you just become to be a summand inside here. So we can call this is like a monster homotopy group. So the machine, the work is aiming to this one. I actually chatted with Pedro. The second part is also works. Use the same methodology. Okay, so that's how the idea of this program design, because we really want to touch with the depth of the homotopy theory. Okay, so now I think because of timing, I don't want to explain more detail, so I have to move to second part of the talk. So now backwards to the question: how can we do the topology for AI? Right? Okay, so now of course topology for AI. There's many ways to understand. I choose the way. That's my views. I will think about like not just the same in the neural network, and you try to develop a model. Instead of this, we're also including like for data analysis. Okay, I will think about this part of the picture. So in this case, then there will be a lot of work topology can do with broad view. Say one is like actually we have done a lot is given a data which I take a topological feature, and then we use, I think previously we use a lot, just use a convolutional neural network, and we use machine learning, and then we got the analysis, right? And now actually we are moving some directions. We try to insert the topological approach inside the deep learning, so we get one package together. And I think we also have some ideas. Now it's moment, I say only in the stage of ideas, we try to work directly into the AIs on that. Hopefully in future we'll do that. We get okay. And so this now let me show a bit. Now all these models, actually we approach it through the way of the complex network. Okay, so we'll try to back to that. Now, either whatever you use neural network, or you use data analysis, or we think about kind of graph theory modeling on these data, or whatever you want. And the fundamental question is, how can we understand the complex network? And then the crucial point is the so-called higher order interactions. So that will be the main, most challenging problem in complex like science of network science. Okay, and of course, in recent last few years, people pay a lot of attention on this, and actually a lot of research on this topic, right? You even give Nobel Prize on this topic. So this does mean that this topic already is well established. So far, in this area, for you try to detect the high order interaction structures, right? The mathematical tools are limited. So for pairwise, we have a lot of tools from graph theory, so people can use it to do that. Now, if you look at the higher order, well, it's quite, you will see very few. Okay, few means you still have some method, but compared with graph theory, really limited. And the question is not simple. If you use traditional applied mathematical method, well, then what? Well, people, you see the three-body problem in physics still open. Okay. In other words, you have something still have a mathematically, it's very challenging as well. And now so that means that you should try to develop some idea. Well, we don't want to step back. We still try to look at what's going on for high order structure, right? Although like three-body problem still open. Now, there's one point is, well, that's from my views, is that traditional applied math is focused too much on local analysis. So in that case, you get stuck, like even for three-body problem. You need something, if you get, say, it's a big data, it's a very extremely high order, you may maybe catch some core features to get some global properties, right? And that could be hope, or you try to go that direction. Even although you do not know quite well on the local information, but you can divide something on the global structure, right? And so that's actually these our ideas try to work. And this is just say people in like Longlin and Carlo will be very happy to support this kind of research. So the network scientists, they will be give a high expectation to algebraic topology. Well, in the end of my talk, I also mentioned knot theory. We try to move in that picture as well. But there's, let's say, people is really expect that topology can play something, right? This doesn't mean that, that means what? We already give extremely well, but people hope we can do. So to our mathematicians, this is really good. We are excited that people can try that. But on the other hand, we get high pressure. We should really work out something good, right? So let's the situation. And okay, so let me try to think in this direction a little bit further. Okay, so now let's back to more. Let's try to use mathematical understanding. Okay, so you talk about high complex network, right? So we try to apply, well, we try to see whether we can do anything from algebra topology or from other topology if you want. Okay, so with actually there's a lot of people, I listed some possible chains. So there's one method that people actually studied already, actually a lot of research now. Instead of use graph theory, let's try to make a, simplicial complex modeling. Right? Yeah, in other words, you can, by means of high order, you think about it. If pairwise means A and B, so there's an interaction, let's draw a line, right? Now, it could be possible I have three guys, they interact with each other, right? So let's make a triangle. And in the definition of abstract simplicial complex, this is by definition just a collection of a finite set. And there's a rule in here. So means that any should be closed under subset operations. In other words, if A, B, C is a choice, finite set, then A, B, A, C, B, C should be everything should be all subsets should be inside here. And this is actually if you get back to the algebra topology, this is the beginning notion of algebra topology, so-called simplicial complex. Okay, there's a geometric version and the algebra version. And so once you get models by this, definitely a lot of algebraic tools for algebra topology can get into the picture, right? That's good. And I say that, well, from the practical situation, actually people want to be your model as broader as possible. So in real world, it may not be so good like exactly given a simplicial complex. So For instance, like, well, there's typical example, people choose like a co-authorship relations. So if you take a co-authors ABC, maybe have a co-authored paper, but the AB may not have. In other words, there's some phases missing. And this is actually important. If you go to, say, for example, you go to protein ligand, you want to look at the interactions instead of, say, whatever point. In that case, your choice of finite set should be some chemical elements from the protein, certain chemical elements from the ligand combined together. So that will feel to be a simple complex, right? And if you look at like a gene expressions from biology, well, it will have some certain gene joined together, you get that expression. Otherwise, sometimes may not happen. So a lot of things of this modeling, from the view, application, they try to make your notion to be as general as possible. And in that case, we have to go beyond traditional algebraic knowledge. So that's a motivation. In other words, we should try to develop, say, for example, homology series of simplicial homology, say, extended to hypergraph, right? So that's it. And maybe there's some structures. So mathematically, you can look at whether there's a weighted situation and the twisted structure, right? So we can produce a lot of tools out of that. So that's like a part of this. And well, there's another method, another approach is even more amazing. Well, I'm not sure both are amazing. Okay. Now, another approach actually for complex network is through a different view. This is something like actually is a model from Lonely Wolf's method. So in this picture, you still use digraph to make models, but you take a multi-layer. So first of all, you have to make a multi-layered diagrams because you're too complicated data. He will be say, okay, let's try to make a clustering. So the typical example, like in China, you have a 1.4 billion population. That's too big. Let's to make a cut by provinces, and then let's continue to cut clustering, make it smaller and smaller until small village. You can see all relationship is quite simple. And so let's make a system of that. Well, that's just certainly the idea. And now there's one important thing. So in this point, you have not seen was there anything in higher order situation. Well, higher order interaction in this model is so-called it's driven by higher order interaction. In other words, there's some ODEs, or you see, well, there's certain, well, I may be moved back. So there's some, you give some ODEs according to some rules, he can have all rules. And this diagram will be evolutionary changes. And the interaction given by some rules. So you get some picture to see that. So you're still a diagram, but you get certain higher order structure inside here. That means higher order interaction. Okay, so now you say that mathematically, actually, you will see that you get a diagram, and you will get age colored, because sometimes the positive interaction and the negative interaction, all these things come in. So you get a different color. That means that the mathematical just color for that, right? And you maybe possibly you get the weighted because you're stronger and the less. That's our understanding. And you get the multi-layered diagram. So actually the system is moving down, and there's certain higher order structure inside, right? And these things, of course, they will be, say, the way will be changes. Okay, look, the way it will change because there's some evolution. Right? From this idea, let's say why we seek that ideas. Actually, we want to, if you look at the neural networks, if you go to AIs, we also want to change the weight, right? Okay, so now, now in this case, now mathematically, first of all, what we can do? Well, we try to, the topology is always a diagram. Okay, the picture is object diagram. So it depends on topology of diagram. As usual in mathematics, topology is first the layer, so you make the topology, and next you get a special rules that make geometry, right? And so you get to understand the structure, and you can understand, and then we need to look at the dynamics as well, and look at the control as well, right? And finally, you may need to try to understand how functions, like how the human beings, the brain works on that. But that will be take all mathematics, get into picture. Now, from the view of a topology, let's first just look at the topological structure. So in topology, there's two things, basic thing, algebraic topology, one called homology theory, another one called homotopy theory. Actually, both guys support each other. Homotopy theory will be support the homology, so-called scientific interpretation. When you describe n's homotopy group, what? That's the balls, like n-dimensional balls, get continuous mapping into that. So you can detect n-dimensional holes or singular holes. And then there's a whole with homomorphism from homotopy to homology. So that means homology, you can do some computation. So that's why I say the homotopy, in algebra topology, actually you have two hands, one supporting another one compute. Okay, so now, let's move it. Okay, so now they move to the question to the more mathematical question, right? Okay, so in our objects, actually, you get some graph. It's actually because of some reason, there's you get a network, like a diagram. Okay, so now we say, okay, how can we develop algebraic topology of that? Well, if you open that one, actually, it's not bad. History, there's an area so-called topological combinatorics. Okay, there's people actually have done a lot of work, even from mathematics, right? Now let's see. Well, there's some classical construction. I just think there's many construction guys did it. People actually did it. Okay, so the one way is one typical one, so-called like a clique complex, and in that case, you just take. You take a look at the graph. Let's simple, take a simple as simple as possible. Take a graph, okay, simple graph. You look at those subgraph, right? Any pair of the vertices has an edge joined together. Okay, let's call clique. Now you get a collection of a clique. So that's a simple complex. Okay, so when you're simple complex, you can do topology. Okay, so that's the approach. And actually, there's a quite well known in mathematics, but for people out of mathematics, maybe less known is so-called the neighborhood complex. And this is actually amazing work from the Leve's for his solution on Nice conjecture. This is the foundational work of the area of topological combinatorics, right? And he really introduced a method that use homotopy theory to solve some, say, Nice conjectures. But and they explain general one, okay? So-called like home complex or graph complex. Actually, a lot of notion coming. And now, I just make a remark. There's, if you look carefully, graph complex. There's Jason has a definition, and actually conservative has also a definition, but conservative definition is slightly different. You can look at another interesting point from conservative definition. Okay. Now move to the one, because we want to focus on one particular method instead of like look around everything. So we focus on the methodologies developed by Professor Yao in the Binzer, okay? And this is now it's called the GLMY homology of a diagram. So we just say, okay, let's make a mathematical object just diagram. Okay, so we try to produce homology and homotopy, obviously. And this homology is so-called actually originally called path homology, right? Now it's called the GLMY homology. And I put here is that this homology and the motivation, you can see even backwards earlier in 1990s, coming from the physics. So physicists actually try to develop discrete differential calculus, right? That's their motivation. And then, so as usual, physicists can propose a lot of smart ideas. Okay, we try to make how to approach that. And as usual, physics may not have a real mathematical theory. They display nice examples, has physical meanings, and like that, right? And the story will be, I think the Professor Yao and his will ask the several guys to work on this topic to establish a complete map theory. So this paper has 88 pages to make mathematical notions and the series to do that. And then there are a lot of follow-up work on this one now. So it began to be a new research field. Okay, so now let me say a little bit. Okay, so because just try to explain to general people. So I just say what's the basic ideas here on this theory. Okay, so basic idea, you give a diagram, right? So I get the nodes, points, then take edges and arrows joined together. Okay, that's diagram. Okay, so now how can we do do some algebraic topology? Well, you look at this so-called path complex. First of all, you look at the passes. Okay, so A to B, B to C, and all. This is so-called path complex. Of course, you can do that. There's some background important things of this construction. So now, if you know mathematics a little more, well, when you're working on category, any category, they are so-called nerve complex. And the view exactly constructed by the passes. Okay, so from this terminology. And of course, we look at the diagram as a simple. You can say make a quiver, so you get the multi-arrows to do that. Now, what's the difference between this and the category? So you look at the quivers, so A and B, maybe a lot of arrows, right? In category, a lot of morphisms. And then here's another. The difference between category and the quiver is what? In category, you have a composition. So when you say morphism from A to B, B to C, okay, now you compose. You can do the composition and they join together. And there's a law assuming, right? Okay, so now, but the quivers, there's nothing, no such a So quiver, difference is that quiver is without any composition operation. Okay, and so you can do this the canonical construction from the category theory. Okay, so then you move to look at the quiver. Of course, simple. Let's look at the diagram first, right? So diagram situation is that A to B has an arrow, B to C has arrow. It could happen that A to C there's no arrow, means that there's a composition rule may not hold, right? But this path complex still it can work. And in this case, path complex will not produce a simplicial complex. Actually, for categories, nerve complex is simplicial set, right? So this case may not produce. Then it becomes to be object actually beyond the traditional algebraic topology object. What you can understand here is just a collection of hypergraph. Okay. So because if you look at this ABC of like arrows of A to B to C, right? You get three. Think about that as a two simplex. Then you take all possible faces. A to B arrows exist, B to C exists, but possibly A to C no arrow. So there's some face missing. So it will become to be a hypergraph. And then I try to explain the definition of a GLMY homology in my way, but it's actually the same, okay? So it's equivalent to the Professor Yao's original definition. And well, we can define the homology theory on diagram, or hypergraphs, okay? And actually, let's just follow Professor Yao's idea, and then we can generalize to do that. So now I try to say, how can we do the homology, move to the question, how can we define homology, simplicial homology theory for hypergraph? Okay, so given a hypergraph, that means in our definition, it's just a collection of finite sets. That's all. Okay, no other constraint criteria. Okay, remove it. Just a collection of finite set. Actually, in mathematics, it doesn't matter finitely many or infinitely many. Okay, so just and now what's the difference between this one to simplicial complex? Well, there are some faces from the view of algebraic topology. There are some faces missing, right? So there are some. So I can think about simplicial complex with some missing faces. So first step, I would say let's collecting backwards for all of those missing faces. Okay, so I bring back all of these missing faces, right? So that will become to be a simplicial complex. So it closed up to simplicial complex. Of course, there are people working on hypergraph who will be angry. Okay, well, not working on simple graph. I would say wait a moment. Okay, well, we will do next step. So that's the first step. Once you have simple complex, certainly your chain complex come out as usual, right? So if you're strictly speaking, you have to have simple complex, you have to do the so-called orientation. So you take an ordering on vertices, then you can well define, produce a chain complex, and then produce simplicity homologies coming out of the chain complex out of that, right? Now I say it's not step because I look at the second part, but we are only interested in part for hypergraph. In other words, in a way, algebraically, you can take a linear combination out of that. So this will give you some so-called like a graded subgroup of the chain complex because you get a big of that, right? And this guy here, if you give a linear combination of hyper-edge, it may not form a chain complex. Let's go back because there are some faces are missing. So then you can try to remember when you get into the even high school now, right? Or university, you know, when we learn analysis, people like to learn supplement and infilament, right? So you do that. So what that means, this guy may not be chain complex. Then you try to look at the supplement means the smallest subchain complex contained that, right? So you push down, okay? So let's make it smaller. And then you can look at the idea of an infilament. So it starts with everything to be zero, definitely chain complex. So you move up, so you take a larger subchain complex contained here, right? So I get something may not be chain complex, I can take covers that, supplement, and then bottom that. I would say there's a river could happen. Okay. Now there's actually it's a interesting lemma. It will be a very good exercise. Okay, try to figure out. It's not very hard to prove, but it's really important dilemma. When you observe that the infilament and the supplement, when they do this way, well, of course, they may not be the same, right? But the inclusion induces isomorphisms on homology, right? Okay, so they are same homology. And this can be exactly how you introduce the homology for hypergraph, right? In a very natural way. And extends the simplicial homology, because when you get a simple complex, nothing missing, so river is covered. And that's exactly the original one, right? So this is so-called like what called embedded homology of this one. And I say when we apply to the past complex, that's exactly GLMY homology. Okay. Okay, so now because timing, so I say okay, so idea of that. So this is the homology theory produced. Now I will say there's another thing. Okay, so when we try to produce homology, we try to support. So we look at the homotopy theory. Okay, well, if you're in history again, you look backwards. Even people actually look at the homotopy theory in graph theory, right? Long time ago, even like you know. And now we are more interested in the homotopy theory of diagram. And turns out this theory has been developed by Professor Yao as well. Okay, so it's in another paper. So we are trying to move in this direction and try to work out some homotopy theory on this diagram. Okay, now here's the one thing I try to mention here is that, well, okay, this is a display. How can we produce homotopy? Well, actually, the idea is it's amazing. So how can we do the homotopy of the diagram? So there's a domain called diagram. Okay, so then there's a targeted diagram. You look at the diagram map. That means just vertex goes vertex, edge go to edge. Possibly there are two vertices clapping together, right? Okay, so that's called. And now the point, how can you make a homotopy? Well, homotopy means kind of like a deformation, right? In terms of diagram, you can say, well, what is called one step. So I take a domain G, I take put the graph G on the ground floor, put another copy of graph G on the first floor, okay? So we get a cylinder like that. And make all arrows goes up, right? Okay, so that's the cylinder, right? And then look at the diagram map out of that. And that's the homotopy. Now this has a meaning. It carries a shape. If you see the graph G shape in H, that means you get mapping on there. right? Then you can, well, there's some vertices joined together, so you get a singular shape. And if you draw pictures exactly the shape of, say, F move to G because L move to uniformly. So let's homotopy exactly describe how can, say, subgraphs move uniformly, or if you okay, so now I think once you catch that, you know how can you introduce homotopy. So homotopy, because you want to equivalent the relation, so you allow to be negative way reverse. But if you want to work on dynamics, you can just keep going on that. So this is a nice theory that connect the homotopy theory and the dynamic of laws on the diagrams. Okay. Okay. So now maybe I got time. I move a little bit, right? So this is the basic notions, homotopy and some homology. Then you go to picture in algebraic topology, right? So first one, you look at the fundamental group, okay, so as usual, and that comes out in the directed, undirected graph, is all, everything works pretty well for the undirected called A series, okay. Then directed GLMY theory, okay. So the fundamental groups are good, and the Poincaré lemma is true, so it's verified already, okay. Poincaré lemma means what? Abelianization of fundamental group is first homology. Okay, so that works well. And now the tricky part is about higher homotopy group, right? It's actually mathematical. So there's a notion have been actually introduced by Professor Yao. It's use the loop diagram. I really like that. So they have a lot of work you can do. So this will be something like a loop space. And there's a notion you can say loop diagram. Look at all possible loops. That, right? And that could be recursively introduced higher homotopy groups. And now there's one point I would say the project is here. It will be like we try to describe a homotopy group as like a usual. Usual means that homotopy is a domain, the sphere I'm mapping into a space. So I try to detect the high dimensional holes. Now, in the situation here is that we try to detect some structures in diagram, right? So instead of like recursively define, we try to give an explicit definition of that. So that's the motivation try to do that. So you use like this network. So left side like this is like squares or cubes. Okay, then cut that and then mapping into. So that's exactly what we like use like a cubical description. And that comes out, why I want to do that? Well, this, as I said, when we try to introduce mathematics tools to do whatever in data analysis or AI, so we try to do some scientific interpretation. So in algebraic topology, it is important the homotopy to support the homology. Okay, so homotopy can go to in depth to support that, and there's Holloway's homomorphism can move into there, right? So that's the why it's important when we use this cubical mapping. So go in the structure. Actually, that means that the GLMY homology can detect like cubical structures of the diagrams. In other words, you think about the following way. So I take n-dimensional cube and I take arrows, join that. I'm mapping to the picture, right? I make a boundary to be a point. So that's like in holes. This is like a picture of geometric views of the holes. And homology or homotopy, strictly speaking, homotopy can detect the complexity of, if you get a homotopy group, it's very large, that means a lot of that, right? Or you get a few. So this detects the complexity of these n-dimensional cubical structures of diagrams. And there's a work, actually, this is a really nice work to done, is that actually we work out the pub sequence. So the pub sequence, why it is important? When you look at the algebraic topology, you get a continuous map to that. Then, or in diagram, we have diagram map. First question you need to understand, what's the question from the algebraic topology? Well, in algebra, when we have homomorphism, we need to look at the kernel, co-kernels, right? Exactly. Now, in terms of homotopy theory, you can ask what is a homotopy version of kernel? And that's so-called homotopy fiber. that will produce long stack sequence for homotopy groups. Okay, that's in traditional algebraic topology. So this work says that in digraph homotopy theory, this also works, right? Let's say touch the kernels. So now usually if in algebraic topology, it look at the homotopy co-kernels. That's also another type of pop sequence that will check for homology, right? So this is we work on homotopy theory. So we already carried out this. Okay, so now in the last minute, I try to explain these applications. Okay, well, so there's if you see that actually we studied from a few years ago, and a lot of applications of GLMY homology, even like in network side, right? In networks, and now there's we say the materials, right? That's where this is our group did it, right? Okay, so this is we try to apply to detect the materials. Actually, Professor Feng Pan is already give a planning talk on the material science. And then we will actually work out the applications of the just use GLMY homology to get to go there. It got a very nice result. And we work with learning together, and we make say this called the complex disease. Again, we just use test homology or GLMY homology to test it, how it works. And turns out it's worked out. It's quite perfect. Okay, so let's see, and let me say more. Okay. Now, even we can try to develop a bit of notion. Okay, so we try to apply this series on like hyperdigraph, right? So hyperdigraphs will be what? For hypergraph, you try to make a direction on that. That means assign permutations on the hyper edges, and you can work on this theory, and looks quite good. And yeah, now actually there's another one. I hope that we will get good news soon, right? So far the review is quite positive. So we would try to make knot theory to that as well. So we can go beyond algebraic topology and make knot theory to do this analysis on protein structures. Well, we choose the object of protein structure because we try to make something to be challenging one to test the mathematical method, right? Okay, so now, well, there's another one, right? Found the university here, right? So we also start to look at something like in 2D protein structures. So this is gave amyloid fibril. And again, well, instead of a topology, we can try to combine some geometry, right? So make a discrete version of torsion, and then we try to use some useful tool directly collecting the some like hopping distance out of that to make it. And we can combine all these methods to this method, try to analysis of structures. So far, somehow we are, this is the progress, something quite good. Okay. So we are still working, and we see there's some more. So the more will be, as you see in this stage, we try to look at the topology and the AI, right? So we're testing different methodology for topology. So we can try test it as a hypergraph homology, and we can try to combine hypergraph homology and spectral analysis, and together, even like yeah, I think there's a Docker complex. Some other people also work on that, and we also we also use that to as a modeling and to get good result in biology as well, right? Okay, so now there's a more general. Actually, this construction is more complicated, right? It's in mathematics we like this home complex, and people in applied or out of math may not know this notion, but we try to test it. And so let's and even like we work on like for modify the past complex, we try to make jumpings, right? So you can take hoppings on hopping complex, but the first thing you can do is to make this use a spectral analysis on hopping first. right? And then we can develop like hopping complex as well, because one step, second step will be different. Let me show you a little bit why it's different. So when you look at the proteins in three-dimensional space, that means there's some, chemical elements here, right? So there's a simple idea, geometry must be there. So if I look at the A to B, I just look at distance. Then I look at the B to C is the distance. Now I measure from A to C, right? So if distance from A to C exactly equal to, then together, that means that it goes straight line. Now if less than that, that means you have to curve, right? You're curved. So it's strongly curved, that means there will be like, if you draw the pictures, in protein, they're so-called like backbones. So if you look at this structure, backbone, they are very hard by chemical interactions. So if they are strongly curved, that means they detect information. So that's why if you just simply actually look at the what we call like hopping distance, so you jump it, and easy to compute, and they can see geometry will be inside here already, right? So that's actually we are developing. Also, you can produce, of course, you can take passes. Let's go jumping, right? So all this methodology can be actually developed quite well. And even, of course, there are some others. We tested to say combine like a neighborhood construction and the path complex together. And that's, I think, I try to stop here. Okay. So this is the, in our team. So this is Lonely, right? His picture is younger than he now, I guess. We are working together. So the beings, of course, we are use a lot the theories of Professor Yao. So we try to actually we do the first two collaborations with different areas. So Longlin is a statistician. So he has produced a lot of his own method. Like as I said, his view is different. And now we have some mathematical theories. So we try to work together and learn to play with math and AI. Right? That's okay. So I should finish my talk here. Thank you very much. Yeah.
Do we have any questions for Professor Wu?
Yeah.
In classical homotopy theory, there's a pointed version and a unpointed version. Is there such a distinction in digraph homotopy?
In classical homotopy theory, you talk about which one? Configuration? Or configuration space? Yeah. Or simplicial complexes. Yeah, of course, the simplicial complex, a lot of applications already use a lot. And you see, I'm talking about something, beyond. Currently, the majority of in topological data analysis is use simplicial complex approach. Like even like, the back, like they use like check nerve theories or these things. That, of course, is good. Particularly, as I said, it's quite successful, right? And the point, my talk will say, okay, in addition to these transitional tools, we'll try to look at more others.
I have a comment. If we consider a graph, we may try to consider it as an intersection graph of a chord diagram and then try to calculate something like Kaufman bracket and Khovanov homology. And there are lots of attempts, and actually successful attempts, of spectrification of the Khovanov homology. It means creating some homotopy theory or some algebraic topology from homology. And it reminds me very much those independent sets or those clique complexes you were mentioning here in your talk. So I think that there should be something to play with.
Yes, exactly. So let me see here. Let me try to answer it here. Because there are several things. I mentioned that there's one paper. Let me first show you this one first. Okay. So I mentioned that actually there's a recently finished paper on what we call not data analysis. Okay, so now let me explain a little bit the basic ideas. How can we do? And the testing is for the target in application side is for choose the plotting structure, right? And now the point is the plotting structure, of course, you get the backbone to the core part. Now, if you directly apply knot theory, of course, you can see the knot shape. But the people from applied side said that it will be insufficient to give their information. So they want to more, it's a quantity, there's something to compute, and they can get some features out of that. Okay, so that's exactly what we do. Okay, let me try to address Havana homology later. Let's design our program. Our program will be like this. Okay, so you start with a protein. So you look at this backbone. Okay, so there's a knot inside, or there's a curve, whatever in space. So the protein is sensitive for local transformation, it's continuous transformation instead of global. So it's a different mathematics. So we should look at each of these, go through that way. We take a point, I take a distant circle. So I take a ball, we can cut the knots in some curves inside within this screen, right? Okay, so now the way we do Havana homology is different than next. But first we need to do something it's easy to compute. We don't want to be something it's terrible to compute, that will be bad. So what's the good thing to do? To compute. You have some curves within the ball, Gauss integral. That's it. Okay, so you can compute the integral, simple. And now you make a ball running from this one. So you get the sequence, right? So you get the data, you get the numerical information. And then you make a ball changes as well, okay? So you design such a way, and it's quite successful. It makes performs to analyze protein structure performed much better than so-called TDA, topological data analysis. That's our comparison. So I would say I'm waiting for the good news of this paper. And of course, next one you can do about all space curves, or so a lot of theory from the low dimensional point will get into picture as well, right? Exactly right. So you're right, exactly. Mm.
Any other questions? I think I saw one more hand earlier. So is there maybe one more question? Or if not, then let's thank Professor Wu again.
Okay. Thank you.